All right, happy to welcome you to this tutorial. I want to um, use this as a walkthrough through the py-neuromodulation feature estimation and neural decoding package. This is a tool that was developed in the intervention and cognitive neuromodulation laboratory since a couple of years. And yeah, first of all, there's a documentation available that is hosted through GitHub, where all of the examples usage is described. And also there's a preprint publication where the methods and also some decoding applications are explained. First off, I want to start with the basic data input that can be used for this toolbox. So there's two separation. The first one is offline recorded data. This can be in a format such as EDF, FIF, Brain Vision. Yeah, that is supported by MNE IO. And the second one is online real-time feature estimation. And here we make use of the great software package MNE Lab Streaming Layer. So yeah, online streaming can be obtained through a lab streaming layer stream. Settings are then, yeah, afterwards, settings can be specified with a couple of features. So I just mention here some of them: Fourier transform, wave, band power. We have a wrapper around MNE connectivity, then periodic and aperiodic spectral parameterization, bursting features, and also waveform shape features. There are two specific parameters that I want to point out. The first one is the feature sampling rate. So this just specifies in which interval features are computed. So with a feature sampling rate of 10 Hertz, every 100 millisecond, a new feature set is computed. And the duration for feature computation is specified by the segment length feature. So for example, we compute features with a duration of 1 second. The output is then saved through a format called message pack. So iteratively, features are saved. There's a reason that the RAM would not be accumulating too much features. And afterwards, all of the features can be saved in a database, also in simple human-readable CSV format. The features can then be used for neural decoding. So there we have a couple of wrappers for feature selection. Different machine learning architectures can be passed through the scikit-learn package. And yeah, different states can be decoded for different applications. The Python backend is coupled also to a front end. So first I should mention that py-neuromodulation makes heavily use of the toolbox, the great toolbox MNE Python. In fact, a bunch of features are computed through MNE Python. But yeah, those are then computed as shown on the A panel and visualized also in the browser. And this is done through a fast API backend. So web server is hosted, and in real time, raw data and features are communicated to the front end through WebSockets. And we have then React application, and also we make use of Plotly real-time visualization to plot raw data and features. Okay, I now want to jump to a demo how the package can be installed. So first off, you can go to the GitHub website, and yeah, you can access the GitHub link, and then in the terminal, so this is just an empty directory, you can clone the repository. So just type git clone, and this will download the whole package locally. It might take some time since, yeah, we also ship some example data. And then when jumping into the repository, I highly recommend to use and to install the package installer and yeah, Python virtual environment handler UV. So this one can be just installed by going to an installation page, copying this link, and yeah, pasting it into the terminal. In this case, this was already installed, and we can then install Python in UV by just typing UV Python install. Then the Python version. We can then create a Python virtual environment and also activate it. Okay, you can see that the py-neuromodulation virtual environment is activated. And afterwards, we could already use pip also in UV to install py-neuromodulation. But since we just cloned the repo, we can also simply install the package. So this can be done with UV pip install -e, so an editable mode current package. And yeah, now you can see all of the required dependencies are installed. All right, next we can just type in the terminal the command run GUI. This is internally now starting a lab streaming layer stream. And we will then yeah, open a web browser. Yeah, so this also takes some time now to start off, since the whole package needs to be loaded. But I can already yeah, type that we will just open the localhost website with the port 5001. So you can now see that through some logging that yeah, the loading was completed and that UV core so the web server runs on the specific website. Then we can open it. So here you can see the basic front end of py-neuromodulation. First off, I will start with the offline use case. So we click on select file, and yeah, in fact, can also show that on the desktop I have saved one brain vision recording. So this is yeah, identified by this header file that is read, which I can select now. Click on open file, and then you can see that offline stream setup was successful. Can read also the parameters. In this case, sampling rate of 1 kilohertz was used, line noise of 50 hertz. And we can also specify an output folder. In this case, I will just select the desktop with the yeah, output folder subject. Optionally, we could also pass a decoding model. In this case, I would just run through the channels. So here we can specify the channels that we want to use for feature computation. So if we want to use them, we click on used and set up different re-referencing. So this can be average, but it can be also, for example, here, bipolar re-referencing. So I just pass the channel name of a different channel into this field. In case this is none, there will be default re-referencing. So here I will just go ahead and select the type of each channel. Here this was actually ECOG. So we have a DVS, LFP, and a couple of ECOG channels. Yeah. We can also specify if we want to use this channel as a target. So then we would not compute features for it, and it could be used later on for decoding, and change also the status. Yeah. Okay. Then we can jump to the settings. So this is the whole settings page. Might be a bit overwhelming in the beginning, but you see here a panel of the sampling rate features that I explained earlier. I specify this now to 2 Hertz and the segment length of the features to 1 second. I will then have the option to select different frequency ranges. So those could be, you have a individual band name, for example, with different ranges. I will just stick with those ones. We can then have different pre-processing settings, so notch filtering, resampling, rereferencing, also pre-processing through filtering. So we can use a band stop, band pass, low pass, high pass filter, and also use normalization with a specific time window. Yeah, and also clipping data after normalization. In this case, I will just stick with those and then go to the feature selection. So here I just use FFT settings. I will return a whole spectrum, calculate band power after log transformation, select the mean of each band. And otherwise, yeah, I will use bursting settings into frequency bands. And yeah, so here we can basically select, deselect, and also specify additional feature parameterization on this panel. Next, for post-processing, there are also several methods available. In this case, I will just use feature normalization. So this is similar to raw data normalization. And here I will just specify a time range of 30 seconds where I want to standard scale the features. Can then click on Save and go to the dashboard. So here you can see yeah, the whole range of different plots. And if I click on Run Stream, you will see that in real time data is being streamed. So this is a raw data plot of the available channels. Remember, this was now offline stream. You can see a power spectral density plot and also a heat map where all of the computed features are plotted. Yeah, so here you can see also the ones that we just specified with the bursting settings and also the band power FFT range. Now, if we go to the logging output, you can see also additional information for each time point, how long the feature computation actually took. So this was fairly quick, below or mostly below 10 milliseconds. And it also says where the features were saved. And this was, in this case, on the specific path. So we can go to the desktop window and yeah, first also see that the logging output. And then with the subject name that I provided, we have a couple of different files. The first one is a CSV file with the channel parameterization that we performed in the GUI. And the second one is a feature file. So this is the columns are different features. And if I scroll all the way to the right, you can see here on the right also the time. And yeah, so for each time point, we computed features which are separated by the channel name. Then the feature modality, so this yacht features, and then some sub-feature parameter, complexity, activity, raw data, band power, etc. It's also possible to see the settings that were loaded. In this case, I will actually go ahead and open VS Code. So yeah, here you can see, sorry, I will just open the file of the settings. Mhm. So this was on the desktop under the subject name, and the settings are saved either in JSON or YAML form. And here you can see dictionary like output of all of the settings that we've used and all of the settings that can be parameterized. Those settings are actually rendered automatically through the GUI. So yeah, we can now go back, and I want to show you the real-time stream simulation. So I click on LabStream layer stream and also search for available LabStream layer streams. Now I actually simulated one stream using the same data that we just saw that was offline saved. But now it's the exception that, yeah, through FTP, LabStream layer actually runs in real time. I can connect to the stream, and then you can see that the stream was connected successfully. Can again select a couple of channels. Yeah, now I just select 2 channels, go to the settings. In fact, I will just keep exactly the same settings and then just click on Run Stream. So now we can also log into the terminal, and features are in exactly the same way computed in real time, actually. Yeah. It's also a visualization of the used band power for the heat map. Yeah, can see here that automatically features are displayed. We can also plot the whole spectrum, the FFT spectrum. And yeah, go back to the subject folder. So now it was actually overwritten in this case because I kept the same name. But that's the same, yeah, the same pipeline. Now I want to show you one additional application, and this is actually through also real-time lag streaming layer analysis. And I will open for that the Open BCI GUI. Maybe some of you are familiar with it. So it's a really nice GUI for automatic connection to one of those Open BCI headsets. Right now I will just connect to it. So I have a serial connection, click on auto connect. Now it's scanning for the available Python board, and I will actually put this on. We'll connect also the reference to the earlobe. Okay, now that we have OpenBCI running, I will start a data stream. You can see here that there's already some very nice plotting available. You see in real time the data change. I will now go to the networking part panel to show you how you can start within the OpenBCI GUI LabStream layer stream. So you go here to protocol and then select LabStream layer. And here's already stream 1, 2, and 3. I will only select one data stream and then go down to time series raw. And here, don't change the type EEG and just click on Start LSL stream. Now we can go back to the py-neuromodulation front end. I will click again on LabStream layer stream and search for available streams. So this gives me now a list where I can also see the stream that we just created in the OpenBCI GUI. I will connect to the stream. It says that it connected successfully. And just give it a different name in this case. Select channels that I want to use for feature computation. Select again the settings that we specified. And now I can start to run the stream again. So you can see in the terminal that we started the computation. Those channels are not completely matched with the correct impedance or adjusted for a good quality. But you can see here the live plotting of the power spectrum and also the features that are computed in real time from the stream. So it's a similar functionality as before with the simulated stream. Okay, I will now stop the stream and have a look again at the output. So you have a new subject folder and also have a new feature data frame file where all of the time points are saved and all of the computed features for the two channels that we selected. Okay, as the last part, I want to show you now the backend. So you can see here that I just opened in VS Code the package that I just showed you. Inside of the package, there are a couple of example files. So I will just open the one that is also used for generation of the GitHub hosted documentation. So I will just put a breakpoint at one point and show you how we can debug the this file. I selected here the virtual environment that we created. Maybe, first things, we import the package, we import matplotlib, scikit-learn, and we use the py-neuromodulation IO module to get the example data path. So this gives us a specific one name. I can also show you where this data is saved. So this is just in the py-neuromodulation package inside of data. And here's the subject, which is saved in bits format. And here in Brain Vision 1 recording was saved. We can then use this run path to read additional information through bits. Now we have an MNE IO raw array, and we also have access to the data. The data is just channels times time points with specific sampling frequency, line noise. One thing I want to show is that there's already very useful functionality just through MNE. So you can call here, for example, just MNE plot. In this case, I will try also some scalings for the eCog type, so amplified, and also for DBS type. And this will start an MNE Qt browser. We can actually have a look at this here. And we can navigate it. So I'm pressing plus to increase the amplitude. The most upper channel is the movement trace. And below we can see 6 eCog channels and then 3 DBS LFP channels. We can navigate through this data. So this provides very useful values already for artifact annotation, for checking for signal quality, and for potential features that we want to compute. So in this case, you can see here, just by bare eye, that the amplitude during movement is reduced, and also there's a decreased beta power and increased gamma power. So we can close this window now, go back to VS Code. In VS Code, we identify the channels. So this is exactly the same as we did it in the GUI. So the channels are the pandas data frame with the same um, properties and columns that you've seen before. There's also some plotting that is shown here, but now I want to show you how to access the settings. So this can be done with nm.nm settings. There are different methods to compute the settings. In this case, it's just default settings that are for fast computation. When we want to change the settings, we can just access it through the pydantic settings classes. So for example, we can say settings.features.weight FFT equals true or false. Can specify the different, for example, coherence channels, the frequency bands, temporal waveform shape features that I will execute now. Then we can start a stream. So this is calling the initialization of the stream object. We pass the sampling rate, we pass the channels, the settings, the line noise, and this is optional, but also the coordinate list. Afterwards, we just call stream.run. So here we actually call the data. The data, as you've seen before, is just a 2D NumPy array, channels times time point. We pass an output path, a run name. So now going into the terminal, this was fairly quick. All of the features were computed. The output is also the features data frame. And yeah, so here all of the rows, we can access the time column and also all of the feature names as shown before. There's also one feature reader module that can be accessed through NM analysis. I will call this now, specify also a label name that we computed. So this was the movement right, movement trace channel. Yeah, and then we can plot the target averaged channel. So you can see this here. We can see the individual traces of the target and above a heat map of the averaged batches for each feature. Afterwards, we can also plot all of the features. So this is one visualization of the whole duration. This is also useful for investigation. Here we actually computed also temporal waveform shape, bursting features, and a couple of others. Can plot also the correlation metrics. So this is useful for investigation of correlated features, potentially also for feature selection. And now we can jump to decoding. So here we initialize a scikit-learn linear model. And then we initialize the NM analysis decoder. We pass the feature array. So this is just what we computed beforehand. We pass also the label. The label also has a specific column name. So this is the movement. We specify the used channels where we want to estimate decoding performances for, and also scikit-learn metrics. This is regression problems. So we pass also the R-square score and a model selection cross-validation. So you can see that this is a shuffled threefold cross-validation. So we initialize this decoder and run the machine learning model. We run it for channel estimation and also for all channels combined. We then get a nested dictionary as an output, but we can also return it as a data frame. Now you can see for each channel training and test set performance. Uh, yeah, and I think also a couple of others. Yeah, the subject, channel type. Yeah, but in this way, it's fairly simple to obtain neural decoding performances for a set of channels. We can then plot the results. So this is shown here just in a box plot, um, a, a square correlation for all channels combined or just individual channels. All right, this was just a very simple walkthrough through one example. Also want to show you that this documentation and this example can be accessed through the documentation. So all of the features are explained in detail, all of the settings, the pre-processing, post-processing. And there's also example page that you just saw that is automatically rendered to show exactly the same plots with a couple of different features, how to add individual features, how you can use lab stream, layer stream, also how to use the great package Zebra, so for one machine learning decoding type, how they can be used yeah, for deep learning neural decoding. It's also a page that explains in detail the graphical user interface, the API documentation, and also for contributing. Yeah, I would be very happy to get in touch if you have questions about the toolbox. I would be happy to set up the code for examples. And yeah, by that, thank you for listening and joining this short tutorial. Thanks.